Okay, so this is where we left off last time. 21. All right. So this is that. Remember, last time we had left off, we had been talking about this, but we hadn't gotten to the diagram yet. So this is that diagram for the pathway we had done in discussion method. So again, this is going to be during exercise or fasting. Excuse me. I have to sneeze, but it's not coming out. So the glucagon or epinephrine is going to then activate the protein kinase A. This protein kinase A is going to be working on two different pathways because you need to both, you need to make it so if you switch off the glucagon production or the glucogen production, you're not also still making, you're not going to be making more. Does that make sense? You can't have both parts of the pathway doing different things. And so this is going to be the active right here. That's the glycogen binding region right there. And this active PP1 is then going to be phosphorylated for the GM right here. That's going to split this PP1 off. And this PP1 will be the less active form that's not bound to the GM. Now, this right here is the additional phosphorylation that you can see here, where we can phosphorylate the PP1, and we can actually take it from a less active form to an even more inactive form. And this one's kind of interesting because this is actually going to have the inhibitor, where you're going to be phosphorylating, and this is actually going to stop the active site. And stopping up the active site is one of the few ways of getting basically zero activity from one of these. Okay? If you're wondering why it has some activity, normally that's because we're just having a slight difference, which makes that active site less accessible, but there's still some accessibility to it. Anybody have any questions about that? Yeah, double phosphorylation. Okay. So when the blood glucose concentration is high, your insulin is going to inactivate the glycogen synthesis kinase. This is through a tyrosine kinase signal transduction pathway. The stimulates the synthesis of the glycogen. The inactive kinase cannot maintain glycogen synthase in its phosphorylated inactivated state. The PP1 is going to dephosphorylate the glycogen synthase, activating it and restoring the glycogen reserves. Insulin also will increase the number of glucose transporters in your membrane. And this is what you're seeing right here. And so this is that insulin right here. It's going to bind to this right here, which is that transmembrane protein complex. And so the insulin receptor substrate, which is the IRS, can be phosphorylated. This is going to then give you the, after several steps, the protein kinases. The protein kinases are going to work on the glycogen synthase kinase. So the glycogen synthase kinase is going to be the less active form. Now note that these glycogen synthase kinases are going to be the ones that would have taken that glycogen synthase A and went to the less active form. So you'll still have your PP1 converting those to the A, the more active form, from that B, which is the less active form. Okay? Now, again, this is that insulin binding that's inactivating the glycogen synthase kinase. This is that series of pathways that it goes through. That's the cascade, if you will. The amount of liver phosphorylase A decreases rapidly when the glucose is infused. The glucose binding is going to shift from the phosphorylase A, from the active R form to the inactive T form. The PP1 is going to dissociate, converting it to the phosphorylase B. After a lag period, the amount of glycogen synthase A is going to increase. This is going to result in glycogen synthesis. The released PP1 is going to dephosphorylate glycogen synthase, which will convert it, the glycogen synthase B, to the more active glycogen synthase A. And so we're just looking at the same thing we talked about just now. This is the glucose added at 0 time right here. And so we add glucose, and what's going to happen? What does your liver do when it has glucose available? Fixes the glucose into the glycogen, right? Okay. And so what's going to happen is this is going to cause a cascade, which will eventually lead to conversion into the active form of the synthase, right? And so we're going to have a ramp up. It's going to be fairly rapid and exponential for active synthase, right? That's what you're seeing here. That's that A versus B. Now, if you're having a ramp up of the synthase, do you want to also have something that's splitting and taking away glucoses from the glycogen? Not going to make any damn sense, would it? And so what we're seeing here is that same process, actually a lot of those are overlap processes, is going to actually cause this phosphorylase A to be converted to phosphorylase B, which is the less active form, right? And so what we're getting here is we add glucose around that liver cell, and this liver cell is ramping up glycogen production and ramping down, splitting off the glucoses, right? Okay. So there are approximately 10 phosphorylase A molecules per molecule of PP1. The activity of the glycogen synthase can begin to increase only after most of the phosphorylase A is converted into phosphorylase B. This lag actually prevents your two pathways from operating simultaneously. And so it's that lag that keeps that from overlapping. Okay? Okay. By the way, has anybody ever tried to rapidly type something? What happens if you start getting too fast? Yeah, you mess up and you actually can hit multiple keys at once, right? And then it has a lag, doesn't it? Okay? And so most keyboards actually have a lag built into the keyboard that if you press one key, you can't press another key for a little bit. It doesn't count that one. Okay? That helps you type. I know, right? Weird demonstration. Probably could have come up with something a little less weird than that one. So the glucose regulation of your liver glycogen metabolism, here's that nice beautiful graphic here. Again, we have the glycogen phosphorylase A, this is the R state here. Here we have a glucose. Again, that's the glycogen binding region down here. We have the phosphorylase binding region. Okay, and so your glucose is going to come along. This is going to bind up in here where there are the little red sites that match the color of the glucose. Makes it easier to find. And these are the bound ones right here. And so what we're going to see here is we're going to get a split off. We'll get the PP1 and the GL here. And we're going to get the glycogen phosphorylase A. Now, notice that we still have the phosphates on here, don't we? Okay? And so this is the T state, which is favored by the binding of your glucose. But if we hydrolyze those phosphates, we can get the B state, the phosphorylase B, that's in the T state still. Okay? Now, this one right here is the glycogen synthase. So this is actually going to act on that glycogen synthase. It's going to help you hydrolyze that phosphates, which will convert this to the glycogen synthase A. And so note that we're actually doing dual purpose with this complex, aren't we? Okay, again, we're activating one route while deactivating the other. Okay? I know that's like the theme of the chapter, right? All right, so the von Guericke disease, it's characterized by the distended abdomen caused by enlargement of the liver and pronounced low blood glucose between meals. Causes of the disease. You have the liver that lacks the glucose 6-phosphatase, a mutation in the gene encoding the glucose 6-phosphate transporter, and mutations in other essential proteins of the system. So these are different causes of that disease. Remember that, okay, so the terminology for biochemistry in medical field can be a little bit loose at times. So remember that diseases are, in their root thing, they're effects that the humans have that happen to them, right? Or effects that an organism have that happen to them. Typically negative, right? Diseases are not causes normally, okay? So like if you talk about cancer, it has hundreds of different causes, right? Okay, and again, you can have many different causes that result in the same disease, right? Okay, so one thing to be kind of careful about, it's a common misconception that people make, okay? Pompe disease type 2 specifically is going to be characterized by lysosomes that are engorged with glycogen, and we can actually see this over here, specifically here, and these are the important parts of that. This disease is going to occur when the lysosomes lack an alpha-1,4-glucosidase, which is the hydrolytic enzyme confined to these organelles. Yeah, apparently I got my slide duplicated. Did I just straight up duplicate my slide? Yeah, I did, didn't I? Oops. Okay. All right. If anybody wants to remind me, Dr. Clausen, you duplicated number 2. Number 1 and 2 are the same damn thing. And figure out what the hell was I putting on that. That would be helpful. Anyways, this actually sums up everything about these in a very nice tabular format, which you can go through if you are interested in glycogen storage diseases. Okay? Anybody have any questions about that? Okay. Yeah, there's no possible way we could cover all of this sort of stuff within a semester, right? I don't care how many credit hours this is. So this is the sort of reason why I recommend you buy this textbook or an older version of this, because this is incredibly useful later on. Like you can use this through your career to help you along with, why am I seeing this? What the hell did that mean? Okay? Very useful book.